Hello, I'm James Wotton. I work at IBM Quantum, and one of the things that I do is contribute to our open source textbook called Learn Quantum Computation using Qiskit. One of the things that I contributed is available in chapter 9, which is games and demos, and it's called the Hello Qiskit game. It's basically a set of interactive exercises. It has these code cells here, which if you click run, it will run that code. And if you re-click the second one, it loads in the tools that it needs to implement these exercises. And then we can move on to actually doing some exercises. So what I'm going to go through today is level 1. Which is an explanation of bits. Now you probably know bits. They are the basis of computation. Our normal computers work on manipulating information stored in bits. And much is also the same of quantum computation, which is what, of course, Learn Quantum Computation using Qiskit is all about. The difference is that the bits in quantum computers are quantum. They can be manipulated in quantum mechanical ways. But in order to get on to learning about that, we first have to think about how to manipulate bits. So that's what level 1 is all about. Also, whether we're looking at quantum bits or normal bits, we need some sort of mathematical framework in order to reason about them. Now, for quantum bits, we usually use linear algebra. But I don't think it's the most accessible thing, and it's certainly not the most fun thing for someone taking their first steps into quantum computing. But you can also represent all of the same things, at least for simple cases, using visualizations, and I think they're a good way to get started. So another thing that level 1 introduces is the visualization that we'll be using in order to talk about qubits, about quantum bits. But it will be doing it in the simple case of talking about just bits. So let's get on with level 1. We have a sequence of puzzles, and each of those puzzles ask us to do something, and then we move on. But they also teach us something, and you can see what they teach us by reading the intro and the outro. But I'm just going to say these things to you essentially in this video, so you don't have to bother reading them. And the exercise in this case is to use what's called a NOT gate 3 times. So what is a NOT gate? Well, firstly, let's focus on this circle here. This circle is black and it represents a bit. So we have a bit value, and a bit value can take one of 2 possible values, which we can think about as being 0 and 1, or true and false, or black and white, or on and off. It doesn't really matter what we label them as, but the defining point of a bit is that there are 2 possible states. So this is currently in a black state, which we can think of as 0 or off, and we want to do something with this, and really the only thing you can do with a single bit, which is in its off state, is turn it on. And that is done by means of the so-called NOT gate. We don't have to worry too much about why it's called a NOT gate. It just is. If you apply the NOT gate to a bit, it will flip its value, turning it, in this case, from off to on. And if we do it again, it goes from on to off. And then a third time, it goes back to on again. And this puzzle was just to do the NOT 3 times, so it wasn't a very puzzling one. In the second puzzle, we have 2 bits to look at. And it would be lovely if the screen capture that I'm using gave me the cursor so I could point, but I haven't figured out how to do that yet. But I can just call them the bit on the left and the bit on the right. So the bit on the left and the bit on the right in this case are both in their off state. And we have a exercise which is to turn the other bit, so the new bit, the bit on the right, on. So let's do that. We can use the NOT gate on the bit on the right, turn it on. Again, not a very puzzling puzzle. Now we have mastered the NOT gate, we can do something more complex, which is the C-NOT or controlled NOT gate. So a controlled NOT gate applies a NOT to one of the bits, but only if another bit tells it that it's allowed to. So there are two bits involved in a controlled NOT. One of them is the control and one of them is the target. So the controlled NOT applies a NOT to the target, but only if the control is in the on state. So in this case, for example, if we were to apply a controlled NOT with the bit on the right as the control and the bit on the left as the target, then it wouldn't do anything because the bit on the right is in its off state and therefore it's telling the controlled NOT to do nothing. However, if we apply the controlled NOT with the bit on the left as control and the bit on the right as the target, then the bit on the left is saying to the controlled NOT, go ahead, do your thing, and it will do its thing, applying a NOT to the bit on the right. So let's actually see this in action. We choose to do a controlled NOT, and then given that we are only looking at two bits in this visualization, we don't have to specify which one's going to be the control and which one's going to be the target. It's sufficient just to say which one's going to be the target, and it's obvious that the other one's going to be the control. So if we choose the bit on the left to be the target, and therefore it's controlled on the bit on the right, which is off, then nothing happens. But if we do it targeted on the bit on the right and controlled on the bit on the left, which is on, then it does something. It applies a NOT to the bit on the right and turns it on, which in this case was what we were asked to do in this puzzle. Okay, next let's do something else. This is basically just doing a bit more with controlled NOTs. We are asked to do some C NOTs to turn the left bit off and the right bit on. So we have that the left bit is on and the right bit is off, which is the opposite of what we were asked for. So how are we going to change things? Well, the only thing the puzzle is allowing us to use is a C NOT. If it was giving us NOT gates to apply to both bits, then we would just apply a NOT gate to both bits and it would be easy. But we don't have that. We have a controlled NOT gate. And if we control that NOT gate with the bit on the right as the control, then it won't do anything. So let's not do that. So let's do one with the bit on the left as control and the bit on the right as the target, flipping that to be on, which is exactly what it needs to be. Now we just have to find a way to turn the bit on the left off. And now that the bit on the right is on, then it can be used as the control for a C NOT. We can use the bit on the left as the target, apply the operation, and there you go. So there is not a very complex computation, but we did something using multiple controlled NOTs together. Okay, now you may have wondered why there are these two circles on a large board full of spaces where other stuff could go, but it seems rather empty at the moment. What is going on with all that empty space? Well, we are going to start investigating that now. To do that, let's start thinking about what happens if we don't know exactly what a bit value is, but it is random. We are going to represent a random state using a circle that is not white or black, but grey. So this is not a separate state between white and black, but we're using it to represent that it is definitely either white or black. It has to be one of the two or it wouldn't be a bit. We just don't know which it is, and all we know is it could be either with equal probability. So the bit on the left here is random, but we are asked to make the bit on the right random using a C NOT. So let's do that. Well, so what C NOT should we do? Should we control it on the bit on the left or the bit on the right? Well, if we control it on the bit on the right, because it's in the off state, nothing will happen. So that is obviously not the solution. So let's control it on the bit on the left and target it on the bit on the right and see what happens. What we find is that they are now both random, and this should not be a surprise because the bit on the left will have either been off or on. If it was off, then the controlled NOT will have done nothing to the bit on the right, leaving it in its off state. However, if the bit on the left was on, then the C0 will have done a NOT to the bit on the right, flipping it to its on state. So depending on the random value on the left, you will get the same random value on the right. However, that's not entirely clear from this visualization. All this visualization here is telling us is that the bit on the left, if you look at it, it's going to be random. And the bit on the right, if you look at that, it's going to be random. It's not telling you what you might expect if you look at both and compare their values. We know from the way we created this that these random values will be the same. They will always either both be off or both be on. But this visualization could equally be used to represent them being independently random or random and always disagreeing. So how are we going to add this new information to our visualization to keep track of the relationship between otherwise random variables? So to do this, we add a new circle to our visualization. So there is now a new circle which sits above and in between our existing ones. So remember that the two circles that we've looked at so far represent bit values for 2 bits, the bit on the left and the bit on the right. This new circle does not represent a new bit value. It is not a third bit. It is instead just there to represent the relationship between the 2 bits. It will be black whenever they are certain to agree, white whenever they are certain to disagree, and grey whenever their agreements or disagreements are random. In this case, the bit on the right is off, and the bit on the left is randomly either on or off. If it's on, they disagree. If it's off, they agree. So because the bit on the left is randomly on or off, then they randomly agree or disagree, and that's why the new circle in this case is grey, indicating that randomness. However, if we do the C0 as we did last time to make them both random but nevertheless always agreeing, we see that information encoded in this new circle. It is telling us, by being black, it is telling us they are certain to agree. If we were to flip one of their values, then it would mean that they would be certain to disagree. And in fact, that is indeed what this puzzle wants us to figure out. Okay, then on to the next puzzle. Our aim is to turn on the bit on the right. So the bit on the right is currently random, and we want it to be definitely on. Not just randomly on, either on or off, but definitely on. So how can we remove its randomness and make it ordered in the way that the puzzle requires it? Well, what we could do is do a controlled NOT controlled on this randomness and targeted on the bit on the left. And now, whatever the randomness is on the bit on the right, the bit on the left knows the secret, knows what the value is. So that means whenever the bit on the right is off, then the bit on the left is also off. We can also see that they always agree from the fact that the new circle is black. And whenever the bit on the right is on, then the bit on the left is also on. So the bit on the left knows what it takes to definitely switch off the bit on the right, because if we do a controlled NOT with the bit on the left as control and the bit on the right as target, then if they're both off, then it will do nothing and the bit on the right will be off. And if they're both on, then it will do a controlled NOT which flips the NOT value on the right and turns it off. So let's do a controlled NOT, controlled on the bit on the left, targeted on the bit on the right. It turns it off definitely, but we need it to be on, so we apply a NOT, and there you go. Job done. So they are some basic manipulations that you can do with 2 bits, and it's the way we visualize bits in this visualization that we use in Hello Qiskit. that is basically all I want to tell you in this video. If you want to get the second video, don't forget to like and subscribe. And actually, I don't care if you like and subscribe. I don't need to get my stats up for any reason. But you will need to find out somehow if you want to watch the second video. You can also follow me on Twitter. Anyway, thanks for watching and goodbye.